Okay. Thank you, everyone, for coming or for joining online as you could. In these 20 minutes, I will try, hopefully after these 20 minutes, you will understand the title of my thesis. If I manage that, I'm happy. So the title, as it says, is Cloudspotting, Visual Analytics for Distributional Semantics. So in this presentation, if I manage to move the slides. Yeah. I have 4 stages. First, I will explain what the dissertation is for, what the research was for, what it was the goal. Then I will explain the distributional semantics part, what I mean by that, then what the visual analytics are doing, and then finally, what are the main insights of my dissertation. So there's a lot that I'm not going to be saying, but that should be, that's the gist of it. So what is this research for? The goal has been using in distributional semantics for semasiological research. So distributional semantics is a methodology, and the question is how we can use it for semasiological research, and you might not understand any of those words. So the idea is, suppose you want to know the meaning or meanings of a word. What you normally do is go look them up in a dictionary, but someone has to write the dictionary, right? So what do they do? What those persons do is read a lot of instances of the word. Those are occurrences, attestations, read how it occurs in different texts, for example, and try to find patterns and what those different meanings are. But to do that, you have to read many, many cases, which is tiring, especially if you want to do a lot of words. So the question here is, what if we could get the computer to read all those cases and make the groups for ourselves? So the technique that I've been doing research on would take all that text and turn it into dots and scatterplot, where each line of the text, each attestation of a word, in this case is Dutch Hoarder, becomes one dot, and the computer itself, based on, of course, instructions that we give it, groups them based on what are similar to each other, and from them, can we get the senses from that, for example? That would be the initial question. Can we get the computer to do all the hard work of reading and finding patterns, and then we get those patterns and assign or interpret the meaning from them? So that was the question. What is then distributional semantics? What is this method that would turn those texts into those groups of points? So it's based on the distributional hypothesis, according to which if you have words that occur in similar contexts, they will have similar meanings. So when you have words that occur often with the same words, then they should have a similar meaning, and if they occur with different words, they would have different meanings. So that means we can use frequency information, which is something that computers are very good at, to try to extract a proxy for meaning. So that works with vectors. We would have a vector such as, in this case, for the word linguistics, and based on how often it occurs, or it co-occurs next to a language, word, English, speak, Flemish, eat, or many other words, based on how often they co-occur together, we can build a profile. So the description of the term linguistics would be, it occurs very often with language, and not as often as words, and not as often with speak, does not occur with Flemish or eat. Of course, that is based on a certain corpus, on a certain window size, on certain selections. And instead of using the raw frequencies, because words can have very varied frequencies, we transform them with something called PMI, and this is the most technical thing I'm going to show here. Where we take, for example, that linguistics and language in a certain window, in a certain corpus, go together 285 times. And one of them goes by itself 20,000 times, the other one much more, like 15,000 times. And based on how often they occur together, based on how often they occur by themselves, we can have a number, magic number, 4.37, which tells us how attracted they are to each other. And then we can do that with many different words, and we can compare the words to each other based on those profiles that we build of who their friends are, basically. But these are what we call type-level vectors. So we have one row for linguistics, which collapses all the occurrences of linguistics in the corpus. But if you want to know the internal behavior of linguistics, so what their different instances are, what their different senses are, you can have only one vector because it's going to combine all the behaviors as one thing. So we're going to do something else, but first, these type level vectors, so the vectors that have information for only one word, all the negative values are going to be turned to 0, which is also something technical. So let's suppose we want to know the meanings of the study, and we have 3 instances. Would you like to study linguistics? They study this in computational linguistics too. Or I eat chocolate while I study. I didn't say this from a corpus. I produced them by myself, but I mean, that's also language production. So, for example, we could have a vector for the first cases. Would you like to study linguistics? By choosing the context word linguistics and using the vector of that linguistics. And we could take the second sentence and select the context words computational and linguistics and use those 2 vectors to represent the vector of they study this in computational linguistics too. So when you have 2 vectors, you have to merge them somehow. In this case, we're going to just add them up. And then what you end up with is a token level vector, so a vector that represents one instance of study, and that is the merge of the type level vectors of the words in that context. And then you would have 1 vector per instance per occurrence, which are token level vectors, and those are based on the context words that we chose. We could have chosen different words. We could have chosen also would, they, this, eat, while. Which words you choose, with which criterion, how wide your window is, if you have part of speech tags or whatever, those are decisions that you make. And as you change those decisions, you have different results. And those results we called models. And part of my research was seeing what is the effect of making those different decisions. If you have a different context, what is the result? Is that better? Is that better to try to find metaphorical senses or something like that? I'm not going to talk much about those differences, but that is a question, is how do you define context? You don't need to use computational and linguistics. You could only select linguistics, and then example 1 and example 2 are identical, for example. So those are decisions that you have to make, and they give you different results. One of the questions is, how does that work? Which kinds of decision give you which kind of answer? So what happens is you have an original text, you have a token context matrix, which is each row is a token, and you base it on the context, which is not the context of the token, it's the context of the context, because type level vectors. And then you make a distance matrix. So the token study 1 and study 2 are very similar to each other, so they're going to have a very low distance. Each token is identical to each other, so distance is going to be 0. And then you have study 3 is total opposite from study 1 and 2, because they have the different columns are 0, or the columns that are non-zero in study 3 are 0 in the others. Those are like as if it was perpendicular, totally different. And so the distance is going to be 1. But if you have many, many tokens, like 300, let's say, it's very hard to look at this matrix and make sense of it. So that's where the visualization comes in. We have Disney, which will try to get each of those rows or columns and put them as dots, and it will make different tries until the distances in the scatter plot are similar to the distances in the matrix. So it's going to try this one so that the orange and blue one are very close to each other and super far from the green one, and that's a rather faithful representation. The more tokens you have, the harder it is, but that's what we are trying to do, and it's more interpretable or easier to see than a matrix. So that's the distributional semantics part, and the Disney was the bridge to visual analytics. For visual analytics, we have developed a tool that lets us look at the clouds and also at all the different models and their variation and compare them and get information, but it's an analytical tool. It's something that you would look at when you're trying to do analysis. It's not the best way of showing the results, so I'm not going to show the visual analytics. You can look it up online. What I'm going to show is one of the products and the kind of information you can get. So this is a cloud of Dutch Hoarder. So Hoarder in Dutch, so word that has at least it has two homonyms. One has to do with a hurdle, like the ones when you're running and like an obstacle, and the other one is a horde. It's a bunch of people running and like, yeah, barbarians or something. And the hurdle one can be literal, so it's normally in sports context, something that you jump over, or it can be metaphorical, like this is my last hurdle to become a doctor. That would be an example, yes? So what we have here is those are different instances of this word hurdle, and we would like these groups to match the senses. Clearly, the groups are more than the senses, so that is not really working, but it's also not that bad. Yeah, so what this cloud is representing is, for example, you have there a circle, and that circle is, each dot is a concordance, so basically is a more readable version than actually having the sentences. But in the visual analytics tool, you hover over the dot and you can see the context, so you can find that out. And basically, what happens with the visual analytics, after many hours of looking at all the aspects of the visual analysis, what you find out is that the different groups are normally dominated, not always, but mostly dominated by some context words. So what we have here, okay, no, I can't point. So you have a group, an orange group with a red group that where Hoarder is correlated with meter and also with height. And those are normally the sport context of the literal hurdles that people are jumping. So they're talking about races of 400 meters of hurdles. So that's why meter is coming up a lot. The light blue one on top goes with nehmen. So in Hoarder nehmen, and it's normally this metaphorical expression of taking this last or this first obstacle. So in some models, it's not just nehmen, which is this verb to take, but also erste or laatste, so the first or the last one. And this kind of a fixed expression. Yeah. Then we have the yellow one is journalist, but it's also sometimes fans and camera people. And then the green one, we have tourists. So hordes of journalists and hordes of tourists are technically the same sense of hordes, of the mass of people. But an interesting thing is that, so you would expect that journalists and tourists as people are similar to each other, so those tokens should be close to each other. And more or less they are. They're far from the hurdle sense, but they're normally separated. And that has to do with two things. One is the frequency of journalists and tourists. So because they're frequent enough, they're strong enough to bring the tokens with themselves and not let them merge with others. That's one thing. But the other is some distinctiveness, which has to do with the rest of the context. So when you're talking about hordes of tourists, you're talking about a flow of tourists filling the streets and invading a city. With the journalists, you're talking about them chasing someone or surrounding someone, and it's a very different. And so the interesting thing here is those are not two different senses, but those are two different perspectives that you can have on the same sense and that you might not think of initially. So this gives you maybe not the kind of information that you might want to expect when you're trying to look up the senses of Hoarder, but it's interesting about the usage of the word and its combinations. So here we have different senses. They are not exactly, but what we have mostly is patterns. Hoarder co-occurs with meter, it co-occurs with nehmen, it co-occurs with journalist. Those three don't co-occur together. That is also information, because if you have a list of collocates, for example, of words that co-occur with Hoarder, you don't know if they occur together or not. So here you have, this is a pattern, this is another pattern, this is another pattern. Sometimes they match senses, sometimes they don't. Sometimes they have many senses in one group. Sometimes different groups are what we would call the same sense. But still, you have the patterns as information. So what are the insights that we have from here? Models represent contextual patterns. So we started with this distributional hypothesis, where if you have words in the same context, they are going to have similar senses. And then it's like, okay, if that's true, then we can have a technique that represents context and that will represent senses. So does it represent context? Yeah. But not senses. So if you wanted to use this method to automatically have your entries for the dictionary and then you have to assign what sense it is, no, it doesn't work for that. What it does tell you in the clouds in the kind of shapes, because you have, as you saw, the different groups of colors. Some of them are more compact, some of them are bigger, some of them are kind of mixed, some are more distinct. They have to do with the characteristics of the context words, their frequency, how journalists and tourists are big enough to have their own groups, their distinctiveness, how Niemen and Hoch or Meder are different from each other, and so they're going to have different groups, and relatedness. If they are not so distinctive, they're going to be grouped together, for example. So those characteristics of the context words are going to affect the shapes that the clouds take and how you can interpret them. So can we use them for automatic disambiguation? Not so reliable. Depends a lot on the word that you're studying. Sometimes the result really matches the senses, yay, and others not at all. It's almost like the computer is always doing the same thing with the context, and we are the ones kind of arbitrarily, this is a sense, this is not a sense, and so on. It's, yeah, something I'm thinking. But does it mean that we shouldn't work with these models at all? Well, not necessarily. It still has very rich, interesting information about which words co-occur with the word that you're studying, with how much frequency, whether they occur together as well. And you can even compare words to see this one has very strong patterns and this one is a total mess, and I have to manually annotate them there, certainly. In some cases, this can already save you a lot of manual annotation because you have the patterns. And if you use the visualization tools, which I didn't show you, that's going to help you a lot. So thank you very much for listening.